This video is more complex C13 multiplicity, and I'm going to illustrate it in the context of toluene. And in particular, make sure you've watched it after you've done with C13 intensity. Okay, so toluene, as drawn, you should easily be able to identify as containing 5 unique types of carbon. There's the carbon of the methyl, of course, and you would expect him to have a relatively boring chemical shift, sort of at the 20 ppm or so, thereabouts. And then we have the carbon on the ring junction itself, which contains no hydrogen. And then you have these 2 hydrogens, which I'm going to color code as yellow. Then, of course, we have the next 2 hydrogens. And then lastly, we have the hydrogen that's on the plane of symmetry for the molecule. So there's a plane of symmetry that runs right down the middle. So again, 4 unique types of carbon on the ring. There, these two, that one, and 1 that's not on the ring. So there should be 1 right around 20, 30 ppm maybe, and then 4 that are between 100 and 150, give or take, for the sp2 hybridized carbons. So what would we anticipate for each peak shape to look like? Well, if you're looking at that particular methyl group, the carbon involved is going to be split by 3 hydrogens, and so as previously discussed, you would expect that to look like a quartet. The blue carbon, which is to say the carbon with no hydrogens bound of any kind, shouldn't be affected by any hydrogens, and you would expect it to show up as a nice single line somewhere. The 2 yellow hydrogens are going to affect the carbons that they're attached to, but each carbon only experiences the hydrogen it's bound to. So each carbon will be split into 2 lines, you would expect. Same analysis holds for the orange. Each carbon will be split into 2. And then, of course, here, this carbon likewise should be split into 2, but it should be shorter than the other because there's a single hydrogen in this environment, and these each have 2 hydrogens in their environment. Of course, I drew the blue line to be the same height as both yellow and orange for good reason, and that is because this is a single line, whereas these 2 are doublets. And when you take a singlet and turn it into a doublet, it should come into 2 lines that are each the same height as what a single line would be when it's 1 carbon. So anyhow, 1 single carbon, 2 carbons, but doublet form, should have the same relative intensities, which is why I drew these all as having the same line heights. Now, of course, when we look at the actual spectrum, it may not look like that if there's more complicated splitting, because that will split it into smaller lines anyway. But this would be what I would predict. I'm totally guessing on the chemical shift here, by the way. Of course, all of these predictions made assume that we're looking at the hydrogens being coupled to the carbon. If instead we did the usual broadband decoupling and removed all of the hydrogen information, then this would just be suppressed entirely. And what you would expect to see in the absence of the coupling information is going to be a relatively smaller peak for the carbon with no hydrogens bound, twice as tall for the 2 carbons with hydrogens bound that each are worth 2. So this carbon right here with the yellow attached should be twice as tall as the carbon that's in blue. Then this one should be shorter than these 2, but probably taller on average than the carbon with no hydrogens attached. And that's because the way we choose to suppress the hydrogen signal has the effect of making this carbon taller than a carbon with no hydrogens bound. So it's just an artifact of the way we suppress that signal. And then, of course, the CH3 would be further on down and rather more like the carbon with hydrogens attached as opposed to the quaternary carbon, which again should be shorter than everything else in the spectrum, possibly by a wide margin. So this is what we'd expect before we looked at the spectrum. Here, by the way, is the prediction that MNova would come up with, and I am not surprised at all to see that the relative height intensity between the carbons with H's bound that are worth 2 and the carbon with an H bound that's worth 1, that's 2 to 1. That makes sense to me. That's the way it should be. I'm also not surprised to see that a carbon with an H bound and the quaternary are different heights. Again, that makes sense according to what I was just explaining. What is a little odd, although it also makes sense, is that it predicts that the methyl carbon would be vastly higher than you might predict. And again, the way we suppress the CH information in the spectrum has the neat side effect of pumping more energy into the carbons through the H's, and so the more H's bound, the higher the signal will be. Which is mainly why we can't actually integrate C13 spectra. It doesn't work, because we're monkeying with it. We're adding energy, and the more H's bound, the higher it'll be. So anyway, MNova predicts that this will end up higher than it should, almost as high high as the carbons that are worth 2 as opposed to the carbon that's worth 1. That's a little bit of a surprise to me. Now in practice, when we go and actually look at the spectrum, that's not what happens. So how did MNova do? Well, actually it did fine. It did pretty well on the prediction of the aromatic region, but it totally whiffed on that by saying that the CH3 would be as high as it was. In practice, the CH3 ends up as high as the carbon that has an H on it, but it's worth 1, and that's half as tall as the 2 carbon signals that each have H's bound. But of course, this is all substantially higher than the quaternary carbon. Again, this is more or less what we'd expect. So how did we do on our predictions for the proton-coupled spectra? Well, this is a quartet, just exactly like we expected. This is a short singlet, just like we expected, because of course, there's no coupling involved. And then this region right here ends up being kind of complicated. So let's zoom in a bit. Okay, something weird is going on, but here we have 2 triplets that are coupled to each other. Here we have 2 doublets that are coupled to each other, and here we have something even more complicated, but again, that are coupled to each other. And it's actually the fine shape in these peaks that tell me that they are coupled to each other. So the 2 triplets are part of the same peak. The 2 doublets are part of the same peak. Zooming in tightly on the 2 triplets, I will point out that this 160 hertz value between the two is fairly normal for a JHC, for a coupling between a hydrogen and a carbon. And that, by the way, is why I'm identifying these two as being coupled to each other. They have a 160 hertz coupling between them. And then, of course, this messy thing and this messy thing are 160 hertz as well. Okay, so now I want to zoom in really tight on the quartet, the methyl quartet, and let's take a closer look at it. Whoa, so the methyl quartet, every single one of those lines has been split into a triplet. That's kind of weird, but let's take a closer look as to why that might be. So of course, keep in mind that the carbon that we're looking at in a carbon spectrum is this black carbon right here. And if we were doing our standard broadband decoupling, what we would see is a single line on the order of 22 parts per million, or wherever it is that it shows up in the spectrum. However, this particular carbon has 3 hydrogens attached to it. Therefore, it becomes a 1,3,3,1 quartet that is centered around the 22 parts per million chemical shift that it would have in the absence of any such coupling. So again, a 1,3,3,1 quartet right at 22 is what you'd expect from the influence of the 3 hydrogens that are directly bound. And the J value associated with that kind of hydrogen-carbon coupling, which is to say directly bound, is on the order of 160 hertz, as I've shown you. However, the fact that if you zoom in tighter on these, each one of those lines is its own fine triplet tells me that there must be hydrogen atoms further away that are influencing this black carbon. So where do we have hydrogen atoms further away that can reach? The answer is these brownish, yellowish ones out here. These 2 guys, since there are 2 of them, are the ones that would convert this black dot into a triplet. So it's the influence of these further out that are playing the role. Now let's count bonds and see how far a distance that is. So from this hydrogen to this carbon, that's 1 bond. From this carbon to this carbon, that's 2 bonds. From this carbon to that carbon, that's 3 bonds. So these hydrogen atoms are 3 bonds away from this carbon, and apparently that's enough to be visible in the C13 spectrum, although clearly at a much smaller J value than the 160 hertz of being directly bound. In fact, returning to the spectrum here, let's go ahead and measure the multiplicities involved and see what we get. Now, one thing I've learned by doing this is that it's not 160 hertz like I wrote down, it's more like 126, so I should make that adjustment. But then the triplets are on the order of 5 hertz or so. So I should now make a correction to the J values that I wrote down. A JHC 1 bond is on the order of 160 hertz, but in this particular case is 126 hertz. Meanwhile, every single one of the fine triplets is 4.5 hertz according to MNova. And so what we're seeing here now is that the black carbon stops being a single line and becomes a quartet because of the action of the 3 hydrogens that are directly bound to it. But then each and every single one of those lines becomes a triplet because of the action of a hydrogen that is actually 3 bonds away from that carbon. Being directly bound has a very large J value, and there's a large influence from the hydrogens that are directly bound, single bond away, and there's a much smaller influence for the 3 bond couplings. Looking again at this spectrum, I now want to focus your attention on what is obviously the quaternary carbon, given how small it is, and the fact that it is not split into a large doublet. So if we look carefully at this, what you see is it's fairly complicated looking. So why is that? So now, of course, what we're looking at is the blue carbon. And I would simply like to draw your attention to the number of hydrogens nearby that can be said to be within, say, 3 bonds of it. So this hydrogen right here is going to be 2 bonds away from the blue dot. Likewise, you would expect this to be 2 bonds away, 1 bond there, 2 bonds there, and then this hydrogen out here you would expect to be 3 bonds away, 1, 2, 3. This blue carbon has 3 hydrogens that are 2 bonds away, plus another 2 hydrogens that are 2 bonds away, plus another 2 hydrogens that are 3 bonds away. So how many neighbors does he have? Well, he has 5 neighbors that are within 2 bonds of him, and another 2 neighbors that are 3 bonds away beyond that. If we only saw the ones that were close enough, say 2 bonds away, what would we expect? Well, having 5 neighbors would make it look kind of like a sextet. So what does this look like? Well, we have 1, 2, 3, 4, 5, 6, maybe. I'm not entirely sure that what I'm looking at here is a sextet, but it's also not out of the question for being a sextet. Also, it's not out of the question that this could be a quartet or something more complicated, but it's at least plausibly a sextet. And again, if I zoom out to some intermediate range, then you see why I was thinking of this more like a sextet than not. I'd now like to focus your attention more on the relatively nice doublet of triplets thing right here. That is pretty clearly, based on this spectrum, the decoupled spectrum, this is pretty clearly the single carbon with 1 H bound. And it's pretty obvious why that would be a doublet, but let's figure out now why it's a doublet of triplets. Again, the carbon involved is pretty clearly this one right here. You'd expect him to be a single line in the absence of any outside influence. The presence of one single nearby hydrogen should split him into a doublet with a relatively wide J value. In this case, that J value is 160 Hertz. But then, 2 bonds away, what we have are these 2 orange hydrogens. 1 bond, 2 bonds. And the effect of them is apparently to turn each of the doublets into a fine triplet. And the 2 bond, JHC in this case, is about 7.5 Hertz. Finally, of course, I need to draw your attention to the 2 remaining doublets, and there's this horrible looking thing right here that nevertheless has a rough sextet sort of appearance. It's more complicated than that, but it kind of looks like a sextet. And then, well, of course, we have the relatively nice doublets here. So this is a wide doublet with a narrow doublet within. This is a wide doublet with narrow sextet plus something more complicated than that going on. And if we look at this molecule right here, what I'd expect to see is kind of surprising. Because regardless of whether I'm looking at the orange or the ugly brownish yellowish color here, I have a hard time deciding why either of them would be a nice doublet. That doesn't necessarily make sense to me, especially if the other is going to be a sextet-y sort of thing. And the easiest way for me to wrap my head around why I might end up with a sextet is to invoke these 3 hydrogens as being only 3 bonds away, 1, 2, 3, from the carbons in question. And so that gets me to a quartet right there. And then, of course, the corresponding hydrogen on the far side is likewise 3 bonds away. 1, 2, 3. And then, of course, you've got the influence of a 2 bond coupling from this orangish guy. 1, 2. And that adds up to a lot of things, so I could understand why this is complicated, especially because the distance from even the green hydrogen is only 3 bonds. So basically, everything in the molecule could in principle be affecting these red carbons, which is why they might look complicated. But the problem is, a very similar analysis would allow me to reach the conclusion that these orangish dots right here, these carbons, should likewise be affected by a whole host of things. So, can I easily understand what's going on? No, not particularly. So as you can see, I've decided after the fact that this is more likely to be the nice doublet of doublet sort of carbons, and this is more likely to be the doublet of messes sort of carbons. And the reason for that is that these carbons have nearby hydrogens that can affect them much more greatly. I can easily justify why this carbon would be seeing 3 hydrogens here, 3 bonds away, 1 hydrogen here, 3 bonds away, 1 hydrogen here, 3 bonds away, and that total of 5 nearby hydrogens that are affecting it at the same distance should make it look like a sextet. So for whatever reason, the 1-2 2 bond gap to
to this hydrogen doesn't seem to be affecting that red carbon. Why? I don't know. Likewise, if I'm thinking about these orange ones, I think exactly the opposite thing is happening. I think you're getting a 1-2, a 2-bond coupling from this hydrogen to that carbon on either side, and that's what gives rise to the doublet of doublets behavior. And for whatever reason, the 3-bond H's aren't affecting it as much. How good do I feel about this analysis? Not very good at all. But one of the reasons why we generally turn off the multiplicity information in C13 NMR is because of the way in which the 1 and 2 and 3-bond couplings end up being much messier than you'd expect. And for all that proton NMR looks bad, it's actually much more regular, follows rules more precisely. So generally speaking, ignore the multiplicity in C13 NMR and focus more on the multiplicity in proton NMR, because generally we will turn off the multiplicity information in C13 NMR. So my main point here is that coupling is complicated, and trying to understand it does offer some value, but you also need to be careful with multiplicity, because even a relatively simple and straightforward molecule like toluene has within it some complexities. At the first level of analysis, what I'd want you to be aware of is that the hydrogens will influence the carbons that they are bound to, but you quickly realize that things become more complicated in a hurry, because though we have a nice doublet and a nice doublet and a nice doublet, once you start looking closer than that, things get ugly in a hurry. So in practice, what do? We suppress all of the signals. What we end up with is singlet, 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 singlet. And that's because usually what we care about is the chemical shift of the carbon and how many carbons are in those environments. And it's valuable to turn these into singlets for the purposes of analyzing things that way.